Okay, so welcome everybody, and thank you for joining us here today as the World Technology Universities Network marks International Day of Clean Energy. We are very excited about today's programme, having convened 6 expert speakers from across the WTUN's member universities to speak on this topic and on their own areas of research and excellence. Each of our speakers are here as they are a member of the as their university is a member of the World Technology Universities Network. The World Technology Universities Network is a global network of technologically focused universities, and our diverse membership is united by a commitment to the inclusive advancement of sustainable scientific and technology teaching and research, each demonstrating a commitment to a truly equitable innovation for the benefit of people and place. Our members deliver teaching, research, and innovation with a direct benefit to people and society. They drive technical and social innovation and entrepreneurship. They develop graduates who are global citizens and capable of being the leaders of the future, working closely with local, national, and international government, industry, and other organizations, promoting interdisciplinary cooperation and demonstrable impact. Today's program will feature a sharing session by engineers from member universities of the World Technology Universities Networks with the following objectives: to highlight and celebrate advances in science, technology, and engineering in the areas of clean energy, and to share best practice and promote research being conducted at the WTUN universities. This may lead to intra-network collaborations and research partnerships, which is also an added bonus of being a member of the World Technology Universities Network. Just a little bit of housekeeping for our attendees. The Q&A function is activated for attendees, so please do put any questions that you have for our speakers in here. And there will also be short periods of Q&A throughout the schedule that will allow for you to ask live questions to our speakers. The schedule for today is as follows. We will begin with a brief introduction to our chair and first speaker to the event, Dr. Mariyappan Shanmugam from Hindustan Institute of Technology and Science. After Dr. Mariyappan has delivered his talk, he will then introduce each speaker in turn and facilitate the Q&A, supported by the WTUN Secretariat, who will be online throughout. Each speaker will have 15 minutes for their presentations, and we have divided the 2 hours into 3 sessions. So for session 1, we will hear from 2 speakers, followed by 5 minutes for Q&A or discussion. Session 2, we will then repeat and have 2 speakers, followed by 5 minutes for Q&A and discussion. The final 2 speakers will speak during session 3, followed by a final 10 minutes Q&A to the remaining panel, and the event will close at 1 p.m. GMT. So it was with great pleasure I begin by introducing the first speaker and our chair for today's event, Dr. Mariyappan Shanmugam from Hindustan Institute of Technology and Science. Chair, please, you may take the floor.
So thank you, Janice. I will continue. Unfortunately, I'm not able to see your slides. Did you present anything in your slides?
I wasn't sharing anything myself, Dr. Mariyappan, no.
Fine. All right, so let me start then. All right, so good morning, everyone. Could you please confirm that my slides are visible?
Very clear.
All right. Okay, so let me start. Thank you for your kind introduction, Denise. I'm Dr. Mariyappan, Professor of Physics Department in the Hindustan Institute of Technology and Science, which is in Chennai, Tamil Nadu, India. My topic is going to be applications of 2D-layered semiconductor materials in exotronic photovoltaic technologies. So right now, in the photovoltaic technology, we are using varieties of semiconductor materials for energy harvesting applications. Not only semiconductors, we use metals, semiconductors, dielectrics, transparent conductors, almost all sort of materials. I'm going to focus primarily on semiconductors for energy absorption and specifically 2D layered semiconductors, which are emerging materials in the category of layered structures, which are having honeycomb lattice structures mimicking graphene in general actually. So they are all post graphene technology. They have structure like a graphene, but they function in different way. And thank you for the opportunity for the World Technology University Network to present my research in this one. Thank you. So I'll continue my talk in this one. First question that why the 2D layered semiconductors are essential for this application. So to answer this one, the photovoltaic technology means the energy harvesting technology. Right now, we use varieties of semiconductors. If you consider the semiconductors, germanium, silicon, there are elemental semiconductors, gallium arsenide, cadmium telluride, amorphous silicon, crystalline silicon, cadmium sulfide, cadmium phosphide, indium sulfide, indium selenide. These kind of materials are being used to make the junctions with the other possible suitable semiconductors, and they have a specific property called the optical band gap, and they are the responsible parameter to absorb the photon energy. And based on that one, the performance of the devices is being decided. So we call that efficiency. That can be decided, that can be defined the number of electrons that can be generated out of the number of photons that will be absorbed. So to predict the performance of a photovoltaic device, we have a limit called Shapley-Quasar limit. So that is predict the maximum possible energy conversion efficiency for a single junction PN device. Actually, it is primarily dependent on the optical band gap of the materials that's being used in the solar cell or photovoltaic devices. So if you consider the band gap of silicon, which is the dominant material for the energy conversion technology as far as the solar cells are concerned. So the band gap of the silicon is 1.1 or 1.2 electron volt with electron mobility 1400, next model is 168. So all these parameters are very important for the energy conversion technology. And if you consider this material, it exhibits only one value in terms of optical band gap. So one value means that the value is very unique for that particular material and we cannot change it. One means the performance also is pretty set, it's pretty constant. We cannot tune it to a great extent. So that is basically decides the limit of the material in terms of energy conversion. So if you consider the other hand, the 2D layered semiconductors means the topic in this particular session is having properties which are highly flexible. It doesn't matter what kind of properties, it's a mechanical properties or electrical properties or optical properties, they are highly flexible. So if you have a single material which is variable structural, electrical and optical properties, then they are highly suitable for energy conversion technology just because the optical absorption spectrum can be tuned. So if we want to make a junction, then if we consider only one material and if we can stack them with a different optical band gap, then the Shapley-Quasar limit can be broken. So the Shapley-Quasar limit is predicted based on the optical band gap. And in this particular case, if the optical band gap of the material is highly variable, means it's different, then definitely the performance also can be boosted up. So that is the basic idea in this particular case. If you consider 2D layered semiconductor, particularly a material called moly sulfide, molybdenum disulfide, then its optical band gap is variable, starting from 1.8 or 1.9 electron volt to 1.3 electron volt. And in this particular case, the material physical characteristics also varies. Means if it is a direct band gap, then it shows 1.8 electron volt. If it is indirect, then it goes to 1.3 electron volt. So that is also possible to change. In case of silicon or cadmium telluride or gallium arsenide, that is not possible. Band gap is same, and if it is direct, it is direct. If it is indirect, it is indirect. We cannot change that one for any reason. It is natural. In this particular case of 2D layered semiconductor, optical band gap also can be varied, and the physical nature of the optical band gap also changed. It means direct or indirect. That also can be changed. Okay, so that is the advantage, and these are all the 2D layers, hexagonal honeycomb structure material. They mimic graphene structure, but their application is beyond graphene. Unfortunately, graphene doesn't have optical band gap, so that doesn't absorb much of energy in the solar spectrum, particularly the visible spectrum. So we cannot use graphene as a major photoactive semiconductor or photoactive material in photovoltaic technology. So in that particular case, it goes as a semi-metal. So that is being used as an electrode, particularly transparent conductor. So in this particular case, we cannot consider that as a active semiconductor material. So the structure, though the hexagonal honeycomb structure is there, it is not that much useful. So some more material called transition metal digelosinate, they mimic graphene hexagonal honeycomb structure, but they have optical band gap, as we presented in the previous slide. It has the 2D layered semiconductor material like a moly sulfide or molyselenide, tungsten sulfide or tungsten selenide. They have optical band gap. So in that particular case, the values are 1.3 electron volt, 1.8 electron volt, 1.5 electron volts. They are different, and they depends on the thickness of the material, number of layers that's been stacked in that material. So in that particular case, we can use them as a semiconductor, unlike graphene. And they mimic the graphene mechanical properties, electrical properties, just like the hexagonal honeycomb structure. So they are very attractive. They are atomically thin, so we can use them in a flexible devices as well. And in the 2D layer categories, we have transparent conductors, semiconductors, metals, dielectrics, everything is available. For example, hexagonal boron nitride, that is basically a dielectric material. And graphene is a well-known semi-metal or metal. We can use that as a transparent conductor. So the major advantage of this 2D layered material for photovoltaic applications, they are dangling bond-free surface. So once we remove one particular layer, then the materials are free from dangling bonds. So they don't have surface defects in principle. So the defect density is extremely low compared to the other categories of material. And they are atomically thin, so they are highly flexible. They are highly suitable for flexible devices. And if you ask a very specific question, why 2D materials for excitonic photovoltaic technology? Excitonic photovoltaic technology primarily covers the third generation, primarily based on the organic dye molecules and quantum dots based. So excitonic photovoltaic technology, we call that the dye sensitized solar cell technology. This has been reached module level production right now, but they are not available in the market just because they are experiencing some issues. So Sony Corporation, 3G Solar, Panasonic, and Percel, they are all working in this kind of technology to commercialize. The major disadvantage with this technology is the major photo absorption material candidate used in this technology is narrow absorption band. It means they absorb very limited photon in the narrow absorption spectral range. They are not like a silicon or gallium arsenide. And they are volatile. We cannot use them in a very harsh environment, whereas the silicon can be used. And they have defective interfaces, and the process time is a very major big issue. They take a too long time. So 24 hours we need to include the photoactive material into the electron acceptor. So minimum 24 hours means industrially it is not a viable process. So they don't like it. So due to this kind of reason, the major problem with the quantum dot or dye-sensitized solar cells are existing. So we need some potential candidate to replace this organic dye molecules or quantum dot material, and they need to be extremely thin so that they can be coated on other electron acceptors, just like the way that we coat quantum dots and the organic dyes on titanium dioxide or zinc oxide or any other metal oxides, and that can be used in the excitonic photovoltaic technology. So this is a very simple device fabrication procedure to obtain excitonic photovoltaic device. So we have an electron acceptor. In this particular case, I just discussed with the titanium dioxide as a source material, which can be mixed with polyester, and then we can make as a colloidal paste. So once we have the colloidal paste, that can be screen printed or doctor printed on top of a transparent conductor, which has been coated already on a substrate. Most of the time, this is a glass, and then we go for an annealing process. This is a 450-degree annealing process for 3 hours. So once we have that one, we have the structure that glass substrate on which the transparent conductor, either fluorine doped tin oxide or indium tin oxide is coated. On top of that, we have a titanium dioxide as an electron acceptor. So now we have this one as an anode. So we don't call this as a photo anode because we don't have the photo absorbing material candidate in this one. And other than that, we have the structure electron acceptor. So we call that as an anode. So once we have that anode, we need to put that organic dye molecule or quantum dot on top of this one. So once we have that one, this becomes a photo anode. That means it is ready for the photo absorption. So if we have that one, then directly we can go for the device fabrication. Means this is a electron acceptor. Then we need to have the positive hole conductor. So most of the time, in this particular case, it's an electrolyte. So after that, we are going to put the another electrode, high work function metal. In this particular case, it's a platinum, which is coated on the another substrate. So this one is the entire device structure, the glass substrate on top of a transparent conductor oxide is coated. And then titanium dioxide is an electron acceptor on which the organic dye molecule is coated, covered with the electrolyte, which is basically a whole conductor, covered by a platinum, which is a high work function metal to regenerate the electrolyte, and then glass substrate, which covers the entire structure. So this is a entire device structure. In this particular case, we want to introduce a 2D layered material in the second stage, while we prepare the colloidal to replace the organic dye molecules. So that is a major idea. So if we can have that one, the organic dye molecules have the properties of narrowband absorption that can be solved by introducing the 2D layered semiconductor, because they have the optical band gap which are variable in different ranges. So that is the idea. So once we have that one, if we can coat the 2D layered semiconductor into electron acceptors called titanium dioxide. In this particular case, I have coated 2D layered moly sulfide on top of titanium dioxide. So basically, titanium dioxide is a porous structure. It's a nanoporous structure. So we can clearly see from the scanning electron microscopic morphology study. So we have a lot of pores. Through these pores only, the organic dye molecules or quantum dots in the excitonic photovoltaic technology will enter and then adsorbed on the surface. So we have removed those kind of two materials and then introduced 2D layered moly sulfide into that one. So if you look at that one, the pores are still existing after coating also. Means the 2D layered MOS2 is that they are atomically thin. They don't really block the porosity of the material. Means they can cover the surface conformally on top of the titanium dioxide nanoparticle network. So that means it is a very good surface addition, and they are coated properly on the material, as we can see. The lot of pores existing. And if you look at the 2D layered material surface morphology, they are extremely thin. So these are the figure C and D. They show that it's extremely thin transparent layers that's been and then we just want to make sure that it is we have coated this material. So we go for some transmittance studies based on transmission electron microscope, and we have studied the lattice image also. So we have come up with the conclusion that we got some 7.8 nanometer layers coated on the electron acceptors. In this one, we can show that the layers are there. We can clearly see we have taken an individual flake and observed that 7.8 nanometer layer is floating on that structure. So it has been characterized showing that layers. So that is confirmed, and further confirmation to assume that it is a moly sulfide, we went for the energy explosive X-ray analysis, which shows that the existence of the layers everywhere in the electron acceptor. Electron acceptor in general, it is a large area material. We can have 1 square centimeter material. So we need to make sure that the 2D layered semiconductors are conformably covering the entire surface of the electron acceptor. So it is essential to study the energy dispersive X-ray analysis in multiple places, so that we can make sure that yes, the components are there. So in this particular case, so we have concluded, we have confirmed that molybdenum and sulfur are presenting along with oxygen that is coming up from the titanium dioxide itself. So that is clear that the moly sulfide is presenting everywhere in the titanium dioxide. So once we have that one, then we want to go for the optical absorption studies. So the figure B shows that the optical absorption spectrum obtained from the UV visible range, starting from 300 nanometer to 800 nanometer. These are all the optical absorptions of few layers of moly sulfide. And the primary confirmation from here is the 2 optical absorption peak that we have got between 600 and 700 nanometers, 600 nanometer to 700 nanometer. That's a signature peak to confirm the moly sulfide presenting that one. And further confirmation in the Raman spectroscopy. Basically, the titanium dioxide exhibit 4 Raman active modes at 160 to 400, 520, and 644 inverse centimeter, which clearly shows that the anodized phase of titanium dioxide. And further, we have observed 2 optical modes here. It's E2G gas and A1G that correspond to the moly sulfide in plane and out of plane vibration modes that confirms the presence of moly sulfide on top of titanium dioxide. So once we have that photoanode, then we go for the device fabrication, the exotonic photovoltaic device fabrication. and characteristics. So the first A figure shows that the 2, 4, 5 IV characteristics, current voltage characteristics obtained from the excited photovoltaic devices. The black curve is the one which is obtained from a device which doesn't have a 2D layer semiconductor on it, which is purely based on the organic time molecules, which we treated that as a reference device in this one. So if you consider that one, the weight percentage of the moly sulfide in that particular case is 0, and we have open circuit voltage is 750 millivolt with a 13.4 milliamps per centimeter square as a short circuit current density with 73.5 as a fill factor. That shows the photo conversion efficiency 7.4. So that is very clear that we have considered a working device, and then we started to introduce 2D layer semiconductor into the titanium dioxide electron acceptor after removing the organic time molecule. So in that particular case, we have started with 0.05 moly sulfide into that one. So that increased the voltage, and we got a little less current, and it resulted in efficiency 7.5. So that is closely be matched with the reference device. And further, we increased the moly sulfide into the electron acceptor, means 0.2 weight percentage compared to the reference device, and we got a significantly higher current, 15.5 milliamps per square centimeter JC, just circuit current, and the overall photo conversion efficiency for this particular device is 8.5%. So that is basically 0.27 standard deviation with our fabrication. So this is a significant enhancement from the reference device that we have. And when we increased the presence of moly sulfide into the titanium dioxide, 0.258%, the performance decreased and further increased to 0.68%, and we observed 5.8% photo conversion efficiency from 7.4. So this shows that for an optimum value of 2D layer semiconductor present in the electron acceptor, it increases significantly from 7.4% to 8.5. But if you further increase, that doesn't work that way. So that shows that there is an optimum value at which the photovoltaic device can work better compared to the reference device, which doesn't have any 2D layer semiconductor. But if you can increase, then it doesn't work that way, because there is an optimum value at which the photo conversion efficiency can be increased. That shows that the incorporated 2D layer semiconductor into the electron acceptor actively absorb the photons from the solar spectrum very efficiently compared to the organic dye molecules. But when we increase, it impedes the reason is it agglomerates, and the excess 2D layer semiconductor into that one, that doesn't help in the photo absorption as well as charge transfer. So there is an optimum value. Further, we just wanted to justify why this is happening, the enhancement, why this is happening. So if we include the 2D layer semiconductor into the electron acceptor, then we observe that one through electrochemical impedance spectroscopy, the charge carrier lifetime is significantly increased. Basically, the 2D layer semiconductors are getting coated on top of the titanium dioxide, and the band structure is being aligned very well. The conduction band of the moly sulfide is aligned below the conduction band of the electron acceptor titanium dioxide. So once we have that optical absorption, it efficiently increases. In that particular case, the charge carrier lifetime is significantly increased. And if we keep increasing the quantity of the 2D layer semiconductor into the electron acceptor titanium dioxide, then the charge carrier lifetime is falling down. It decreases. The reason is it got agglomerated and it doesn't help in terms of charge transport. So basically, the figure D is the entire scenario. We have an electron acceptor in which the 2D layer semiconductor is being coated, and then we have electrolyte, which is a whole transport layer. So it forms a p-n junction. So once we have the photogenerated electron on top of the conduction band of the titanium dioxide, then it's supposed to be transported to the electrode, which is a transparent conductor in this particular case. And before it is getting transported to the electron collector, which is the FTO in this particular case, we have a surface states in the electron acceptor, which are basically efficiently capture the electrons, and then they are getting trapped in the defect states in the band gap of the material. Once the electrons are captured and trapped in the band gap of the titanium dioxide, then there is a positive holes in the electrolyte. So that also can be captured by the trapped states. Then positive as well as negative charge carriers are captured and trapped in the default state. Then that goes to recombination and we have a charge carrier loss. So we have lost the carrier. So overall, we have reduced current as well as the photoconversion efficiency. In order to affect that one, if we can put the 2D layered material on top of the titanium dioxide, then it can efficiently absorb and then inject the electron, photogenerated electron into the conduction band of the titanium dioxide, and from there it can be collected onto the electrode. So that is what is happening, and the major reason for the enhancement of the performance of the dioxide solar in this particular case is the charge carrier lifetime enhanced in the conduction band of the electron acceptor, which gives the more possibility, more opportunity for the electrode to get that electrons into them. So conclusion of my talk is the performance of the excitonic photovoltaic device can be increased significantly by introducing 2D layer semiconductor into the electron acceptor. By doing that one, what are we doing basically is the increasing the charge carrier lifetime. So that can be confirmed from the electrochemical impedance spectroscopy. So to compare with the traditional structure of excitonic photovoltaic technology, this is very simple and less time consuming. The 20 hours processing can be reduced into few hours, 1 or 2 hours we can finish this work. So that is a major advantage of this work. So that can be directly taken into industry application. So that is the major goal for this particular work that we have carried out here in our university. Thank you, and I'm open for questions. All right, any questions?
We haven't received any questions in the chat so far. There will be another section for Q&A after the next speaker. So Chair, if you would like to introduce our next speaker, and we encourage anyone watching, we have many attendees. If you want to ask a question of either any of our speakers, just put the question in the Q&A and we will return to those after the next speaker.
All right, so I'll go for the next speaker. Dr. Patcharawat from the Department of Mechanical Engineering in Mongkut, University of Technologi, Thonburi. Dr. Patcharawat obtained his PhD from Assoc University, where he modeled and demonstrated voltammetric responses using a combined model of mass transfer and equivalent circuit to include the effects of non-Faraday current. So he is going to talk about heterogeneous electrode structure for future electrochemical energy storage and conversion system. Dr. Patcharawat worked on electrode modification in the performance of electrochemical devices, energy conversion in fuel cells, and batteries. So I request Dr. Patcharawat to go ahead and present his work.
Just to interrupt, the next speaker on the schedule is actually Professor Haslenda, Hashim.
Hello, yeah, I'm Haslenda, but I couldn't open my video.
That's fine. You should be able to share now, Professor Haslenda. Could you try again?
Yeah, sure. I try.
So the second presentation is going for Dr. Haslenda.
It's Professor Haslenda. Then we have Dr. Worawat, Dr. Parvathy, and then in the third section, Dr. Patcharawat and Dr. Christina for the end. So the next speaker will be from Universiti Teknologi Malaysia, Professor Haslenda Hashim, who will be speaking to us. As you can see on the slide, we can see this very clearly now, Professor, the decarbonising industry through floating solar deployment for green hydrogen and power generation. Please, the floor is yours.
Okay, thank you very much, Chairman. I couldn't open the video, right? Okay. Okay. It's okay. All right. So, good day to everyone. I'm Haslenda Hashim from Universiti Teknologi Malaysia. So it is a pleasure for me to present the research title, Decarbonizing Industry Through floating solar deployment for green hydrogen and power generation. Let me. So just to this, sorry. All right. So this is myself. I'm Haslenda. Currently, I'm a chair of Resource Sustainability Research Alliance from Universiti Teknologi Malaysia. And I'm doing, actually my area of expertise is something related to modeling and optimization. And for today's talk, I'm going to talk about how we develop the model of floating solar and as well as integration with the hydropower in order to meet the hydrogen demand and as well as electricity demand from renewable energy, which is solar and also hydro. This project is actually in collaboration with the biggest power generation in Malaysia, and they actually try to explore the possibility of producing hydrogen and also electricity from solar and as well as hydro. So basically, as you can see from this slide, so electricity demand is projected to account over 50% of final energy consumption by 2050. But currently, over 60% of the total global electricity generation is contributed from fossil fuel. And I think everyone knows actually is fossil fuel is actually contributed to the environmental issues. So green technology like renewable sources, for example, like solar and as well as hydro, and green hydrogen is proposed in order to overcome the issue of global warming. And in Malaysia, we actually have abundance of solar. So because we are actually at the tropical countries, so solar is become one of the promising renewable energy in Malaysia. However, due to land limitation, hampered the expanding of solar implementation, thus floating solar is proposed as one of the solutions. So in this study, what we're going to do is basically to develop optimization model of cost-effective of integration floating solar system and hydropower to meet simultaneously electricity and hydrogen demand. So the model will include renewable energy supply. In this case, is solar and as well as hydro. And we also will consider energy storage, such as battery energy storage, BESS, hydrogen energy storage, in order to meet stable electricity and hydrogen demand, because renewable energy like solar will affect the unstable source that caused by weather intermittency. And in this particular project, for in order to produce hydrogen, two different types of electrolyzer will be considered. One is alkyne and another one is PEM. Yeah? So two different types of electrolyzer will be considered. So basically, the research objective is first is to develop an optimization energy model for floating solar photovoltaic to satisfy electricity and hydrogen demand. Second, to determine the least cost pathway for electricity generation and green hydrogen production. And the third one is to perform cost-benefit analysis and greenhouse gas emission assessment. So basically, for the in order to develop this model, so the first part is basically in terms of to understand the problem or issues. So basically, what we're going to do is basically to concentrate on producing green electricity and also green hydrogen production. And in terms of data input, we're going to take the data from literature review and as well as from real plant data. We're also going to consider resource potential and characteristic on site, for example, solar implementation area and solar irradiations, because we're going to focus on one particular area. So we have constraint in terms of land area. And in terms of data input, we're going to include capex, efficiency, opex, and lifetime for solar panel, solar systems, electrolyzer, pump hydropower storage, battery storage, hydrogen storage, and so on. Yeah. And other than that, the data will also take into consideration in terms of electricity price, hydrogen price, forecast of electricity, and as well as hydrogen demand. And in terms of, okay, sorry, because there is a hanging just now. So I'm going to continue. Sorry for the technical issue. And yes.
That's fine, that's fine. That's fine. Yes, we can see. Please continue.
Okay. In terms of technology, so we're going to consider different configurations of the energy flow and as well as technology. And in this particular case, we're going to consider 3 different scenarios. And we're going to develop the models using generalized algebraic modeling systems. And the results that we're going to produce is in terms of overall cost of producing electricity and as well as hydrogen, optimal solar area and capacity in order to meet the demand, optimal battery and pump hydropower storage capacity, optimal electrolyzer capacity, optimal hydrogen storage capacity, and as well as energy and utilization profile. Yeah, and in the last objective, we're going to perform sensitivity analysis to in terms of cost and as well as greenhouse gas. So in terms of model objective and constraint, for this particular case, we're going to minimize the total cost of floating solar photovoltaic system in order to meet 300 megawatt hour, not kilowatt hour, 300 megawatt hour electricity, and also to produce about 5,625 kilogram per hour hydrogens. And for this particular case, we actually focusing on the northern part of Malaysia. Yeah, this is what we one of the area called Kertih, and maximum solar installation area for that particular lake is about 111 kilometers square. Yeah, because for floating solar we not allowed to cover the whole lake because it's gonna disrupt the ecosystems. So that's why normally our assumption is only to cover up to 30% of the total surface area of the lake. And for this particular case, the hydrogen demand is about 5,625 kilogram per hour, and for the electricity demand is 300 megawatt hour. Yeah. So for in these models, among the assumptions that have been made is lifespan of battery energy storage is about 7 years, and annual degradation efficiency is about 3.4%. And for annual degradation of solar efficiency is about 0.4%. And project lifetime is about 25 years with continuous demand of 24 hours per day. Contingency factor is about 20% for all the equipment, and daily average solar irradiation is about 4.7 kilowatt hour per day. Okay. So this is among the data input. So like I said, we actually input few data about floating solar photovoltaic, battery energy storage, for example, in terms of efficiency, capex, price, charging, degradation, yeah, and PEM electrolyzer, alkyne electrolyzer, hydrogen storage, fuel cell, and so on. So this is basically the data input that we input into the model that has been taken from the literature and as well as from real plant data. Okay, this is about the grid in terms of transmission loss, grid in efficiency, inverter efficiency, maximum energy sales to the grid, hydrogen transportation. In terms of pump storage hydro, we consider water tank, capex and opex, and also water pump efficiency and turbine efficiency. Okay, so like I said, we actually developed the model and we ran for 13 different scenarios. So basically for the scenario 1, 2, and 3, we our intention is basically to meet 300 megawatt per hour electricity demand. Yeah. So in terms of the structure, so we considered floating solar photovoltaic, solar inverter, and then it will be supplied to the battery energy storage and produce the electricity demand as required. So basically that we covered here is not considered in this scenario. Okay. So for the second, this is for the second scenario. So we're going to consider pump storage hydropower and produce the electricity. And for the scenario 3, basically is to consider both producing FSPV that supply to the battery energy storage, and as well as to run the pump storage hydropower in order to supply the electricity to the grid. Okay, so for scenario 4, 5, 6, and 7, so we actually considered hydrogen demand with alkaline electrolyzer. So basically in this particular case, like I said, 2 different electrolyzer will be used, which are alkaline and also PEM. And for scenario 4, 5, 6, and 7, we actually considered alkaline electrolyzer in order to produce the hydrogen. Yeah? And another scenario is actually we also considered to pump storage hydropower and consider both battery energy storage and as well as pump storage hydropower, and feed into the alkaline fertilizer in order to feed into the hydrogen storage and fulfill the hydrogen demand. So for scenario 8, 9, 10, and 11, for this particular scenario, we actually consider the hydrogen will be producing using PEM electrolyzer. So basically for scenario 8, the floating solar photovoltaic will feed into battery energy storage, and then it will be supplied to PEM electrolyzer in order to meet the hydrogen demand. So in scenario 9 is considered pump storage hydropower, and for scenario 10, we use PEM electrolyzer to produce the hydrogen storage and produce the hydrogen. And lastly, for scenario 11, we considered to generate the power from floating solar photovoltaic and feed into the battery energy storage, and also supply to pump storage hydropower and use pump PEM electrolyzer in order to produce the hydrogen to meet the hydrogen demand. So for scenario 12, basically we considered both. Okay, we considered alkaline electrolyzer and also PEM in order to produce hydrogen, feed into the hydrogen storage and supply to the hydrogen demand. And for scenario 13, basically we considered everything in this superstructure. So to produce the electricity from FSPV and meet both electricity and as well as hydrogen demand. So this is basically to summarize the scenario from scenario 1 to 13 and what we consider. For example, scenario 1, 2, and 3, we actually want to meet the electricity demand of 300 megawatt hour. And for scenario 4, 5, 6, 7, 8, 9 until 13, we actually want to meet the hydrogen demand. But for scenario 3, we going to meet both electricity and as well as hydrogen demand. And for all, we considered floating solar photovoltaic, but only certain scenario we considered battery energy storage, and only certain scenario we consider pump hydro storage and hydrogen storage. And so we also have different scenario for different application of alkaline and PEM electrolyzer. So now let's move to the results and discussion. So basically, this is a total cost comparison for scenario 1, 2, and 3 to meet 300 megawatt hour electricity demand. And on the right hand side, this is basically the levelized cost of electricity for scenario 1, 2, and 3 in USD per kilowatt hour. So as you can see, scenario 3 is the best among these three because it actually results to the lowest levelized cost of electricity. And this diagram is actually to show you the breakdown of the total cost. And as you can see, actually the major cost of the total cost is from hydro pump storage and as well as the solar systems. Okay, and this is basically to show the comparisons of the results. If, for example, for scenario 4 until scenario 12, using different types of electrolyzer, alkyne electrolyzer, proton exchange membrane, and also a combination of alkyne and PEM. And on the right hand side, it shows the levelized cost of hydrogen in terms of USD per kilogram for scenario 4 and 12. And as you can see here, scenario 11 and 12, 11 and 12, 10, 11 and 12 actually shows the lowest levelized cost of hydrogen. And as you can see, there is a breakdown of the total cost. Yeah, and mostly the total cost is contributed from the solar photovoltaic. Yeah, and this is basically to show the breakdowns of capex, opex, and other expenses for scenario 3, 7, 11, 12, and 13, because this is among the best option to achieve the electricity, hydrogen, and also combination of electricity and hydrogen demand. So for example, like scenario 3 is the best scenario to produce the electricity, and the total cost is about 10 million. And you can see the breakdown and also the what is the significant cost that contributed to the total cost. And in order to meet the hydrogen demand, scenario 7, 11, and 12 is considered the best scenario among the others. And scenario 13 is actually the best scenario for the overall. The reason is because for scenario 13 is actually to meet both electricity and as well as hydrogen. So if you take the scenario 3 and scenario 7, because this is the best scenario to produce electricity and as well as hydrogen in terms of the total cost. So you can see the total cost is about USD 15 million. But for scenario 13, is actually to meet hydrogen and as well as electricity, but it's only incur about 13 million USD. So scenario 13 is actually the best among the overall scenario in order to meet hydrogen and as well as electricity demand. So because if you can see from here, if we actually take scenario 7 and scenario 7 is chosen due to the scenario 13 utilized alkyne electrolyzer, and 90.39% is higher with the additional expenditure of about 1.5 million if, for example, you take scenario 3 and 7. Okay, so this is basically to show you the breakdown of the electricity profile. Therefore, the best scenario in order to meet the power demand, the electricity demand. So as you can see, basically this is the profile of solar irradiation in Malaysia, and this is basically the electricity demand that is required. So this is considered under peak solar irradiation, but during night there is no solar irradiation. That's the reason why the energy is come from the battery and as well as from the hydro pump. Okay? So this is basically at night. So because there is no solar can be accessed during at night, then in order to meet the electricity demand during the off-peak solar irradiation is to get the electricity from hydro pump system. Yeah. Okay, so this is basically the overall electricity distribution for scenario 12 and also scenario 13, where actually we try to meet the electricity and as well as the hydrogen demand, where you can see actually where actually the energy come from, whether it is from the grid, from the battery energy storage, or is it from hydro pump or from hydro pump storage. So it can be illustrated in this electricity and also hydrogen profile. Okay, so as a conclusion and recommendation, scenario 13 is represent the most favorable option for fulfilling the integrated needs of electricity and hydrogen demand, because as you can see, the total cost is around 14 million as compared to the combination of scenario 3 and scenario 12, where it will lead to about 15 million USD. Yeah. So if for future works, so what we're going to do is to optimize the system scalability and flexibility to effectively meet the increasing demand for electricity and hydrogen, while ensuring adaptability to future energy needs, and conduct a comprehensive sensitivity analysis, particularly focusing on the battery unit price and also solar panel cost, and prioritize the continuous research in advanced energy storage and hydrogen production technology. So I think that's all for my presentation today, and thank you, and I'm more than happy to answer your question.
All right, thank you, Dr. Haslenda, for a wonderful presentation on the energy sustainability and environmental planning. The session is open for the question from the audience, if anything. Any questions? If not,
we have Dr. Christina has put her hand up. Perhaps she asks a question of her fellow panelist.
Yes. I do have one small question. Thank you for this super comprehensive presentation, first of all. And I'm wondering, you in one of your last slides, you mentioned the solar panel cost. And I was just wondering, do you have any estimation which area would have to be covered with solar panels to be able to generate this required amount of energy?
Okay. So actually, for floating solar photovoltaic, so we actually I have identified a few lake area in Malaysia, and actually we also explore to use our ocean, to put the floating.
Makes sense, yeah. Mm-hmm.
So basically, so like I said, for lake, we only can cover up to 30% of the total area, because that is basically the maximum surface area that can be covered. Otherwise, it's gonna disrupt the ecosystems of the ecosystem. So, but for the solar, for the ocean, I think in terms of limitation is, of course, you cannot cover. It is a very huge area. But in terms of maintenance, it's quite pricey as compared to the lake, because of the characteristic of the oceans, right? Because of it will become
corrosive salt water. Yeah.
So in terms of area, we have identified a few, and it's actually also among the things that we need to consider is in terms of demand, because this area must be located not too far away, because we also consider in terms of transmission loss and so on. Okay, so I hope that I answer your question.
Yes, thanks a lot.
Okay, thank you.
any more questions? Any other questions?
There's no questions from the audience, Chair.
All right, so let's move on to the next presentation from Dr. Worawat, Associate Professor, School of Physics, Suranaree University of Technology. I'm very happy to introduce Dr. Worawat. He obtained his PhD in physics from Stanford University. He has been a faculty member at the School of Physics at Suranaree University of Technology since 2010. He is going to present his work on the topic of electricity grid optimization in Thailand and the opportunities of quantum technology has been working on quantum states of advanced materials using synchrotron radiation techniques, quantum sensors, energy storage technologies. I'm very happy to welcome Dr. Worawat on board. Dr. Worawat, please start your presentation.
Yeah, thank you very much, Sir Chairman. So today, yes, I will give the talk that especially about introduce something that may help to optimize the energy grid better. Yes, so let's come from I'm from Suranaree University of Technology. So we have some of these projects that work on the clean energy. For example, like this, we have the number of students is about 17,000, and we have solar cell of 3 megawatt on our campus, and that's already been using, and we have like top UI Green Metric University ranking in Thailand. And also close by our university, we also has this national park they call Khao Yai National Park. It's one of the World Heritage Site listed by UNESCO. And we plan to have we have a big picture of what we want to do with the clean energy, and also many SDG that we want to work on. So today I will just maybe a little bit of this that we start. We have a big goal, but we start step by step. For example, we have prototype that clean energy that on the camping site for tourists, that like Lamtakong area that use a lot of we have a lot of tourists that come, maybe like 2,000 people in each weekend, and these come to join and they can use the clean energy for their like charging mobile, and also the backup the office and for like EV. So these are things that we already been doing from our university. Today part will be maybe a little bit introduction that we also have work on like the quantum technologies. This is one of the frontier in the frontier research policy in Thailand. Is Thailand pushed forward quite a bit for the last 4 years or so. And in this, the Suranaree University is one of the leading university that. So I am the head of the project of the so-called Quantum Technology Research Initiative Consortium. So we have around 110 professors and researchers from Thailand, in over different universities, like 19 is still in Thailand. And this we run for 3 years now, and these are more like a bigger picture that we work on hardware computing and a lot of things, and we have application and prototype that and to startup, and the members is 110. That's exclude another postdoc or student for another close to 90 or so. So the besides the hardware, the one that so a lot of things still research with the quantum technology, but the one that got to commercialize faster is from the software side that we can use that for optimization. For example, start from the right hand side, you can use it in the finance to, for example, to increase the efficiency of loaning of the KBTG bank or K-Bank in Thailand, and also the logistics is another option that we been using, and already some exploit some of the quantum inspired algorithm that we use for logistics. So for example, that to see that, and the next one would be about electricity. But let's start with this example. I think it can see maybe you can see the potential. So like let's say that for the logistics, that if you want to optimize to sending a package, like let's say we have 10 points that you start from the same, the starting point and ending point are the same one. Then you're gonna have like about 360,000 possible paths that you can choose from, and this you can look from the longest one. Of course, you probably not gonna use this path. Like in this picture would be 260 kilometers for the longest path, and the shortest path is like 125. But if you use common one, like the sense that you go to where the next closest place maybe is reach about 145 kilometers, which is about 10 about close to 20% of the longer than the shortest. So you have some loose, but if this you optimize for 10 point, it's very easy. Maybe take only some milliseconds. If you increase this by maybe 20 point, a lot of more part, basically 19 factorial, 20 plus 1 and minus 1 and then factorial. So there's a lot of more part. And if you do full optimization, just look at the possibility that you take like 100 years. This is crazy, right? And but I mean, in commercial software, you can be approximate. You have strategic or algorithm to push forward. But this is say that you prepare to lose some of the error or like 10% from the shortest time. So if you come back from logistics, that you can see that there's some problem. I mean, quantum technology can speed that up. Like you can increase 20 point, and maybe it's increase only 2 or 3 times, not like 100 years. So this, if you do this for logistics, it's possible. Energy is almost the same thing. Like instead of sending a package, you're sending energy, electricity energy to the Y. And this has been with got funded from the EGAT. So basically, it is like electricity generating authority of Thailand. Basically, produce more than half of electricity. So we got this funding, and we study the possible what is the important part, and look at the backbone of the electricity in Thailand. So and the thing, one of the concern that I think already Thailand has that a policy that is called 30 at 30. So it means that at year 2030, we're gonna reduce the emission by 30% or so. So that include from the EV cars. So we have to plan to have a lot of more EV by the year 2030. And that's could be, and we already see some reflect from that from policy that subsidize and promote the. So last 2 years, there's only 15,000 EV car purchased, but this year increased by almost 40%. Increased by 400%, right? And that start to getting more concern. And so right now we have about roughly the EV at this is not updated, but I think by the end of the year it's about close to 150,000 EV cars that need to be charged. This exclude the hybrid, just but plug-in hybrid is we need to use electricity. So this come to the question that, I mean, how much the Thailand electricity can accommodate the EV, and this is something that if you use the EV car, you maybe start to see that there's like in Thailand you have like quick charge. There's let's say that you have 5 quick charge stations. If you use at the same time, that we consume the power close to like 100 household usage. So that is something that is scary a little bit. So from the look of this, so we do optimization and see what would be. I mean, if you increase the number of EV in Thailand, and also include also the renewable energy like solar cell, solar farm, how much it can accommodate. So we see the first result is not a lot. Maybe it's only maybe 5 to 10%, about maybe close to 10% that you can replace the normal gasoline car with the EV car. So this is something that we look into the possibility that like expand this kind of capacity that will accommodate EV car. So we look into like virtual power plant, and then where to put basically the virtual power plant is just energy storage, that like the battery that you can put, and you can put the energy in it out, and that's you can expand the capacity. But then of course we need to look for the economic dispatch for that. And we done this for the high voltage. We do for the it's only the software part, but the low voltage where it reduced down that goes to the household. We have some of the tests that we have a site that have about 10 household that we just started there, and we already see some of the possible of how to optimize and help things to make the power stable and not gonna increase the risk of the power line and have a shortage of power or the over current in the wire of the grid. So these are the preliminary result that we see if we can optimize the voltage. These are a lot of lines mean that for each house about 10 house, and if you don't optimize, it's very fluctuate. I mean, like when you have solar cell that put the electricity back to the grid, then if the voltage is keep increasing to the past the threshold, then it will shut down. So this causes a lot of fluctuation in the power, and if you see that after 1310 it's flat. This is because the optimization that you can put it in and try to make everything smooth. So the flat line means the power is really control and we are really stable and also it's not cause the overcurrent. So this is just small power, but it's already we learn a lot from that. In the next stage that we gonna have plan that maybe this besides the grid, we also have looked into the off-grid or the hybrid of that, and there's a number of things that you can fit in like solar cell, battery, car or motorcycle or like this small EV. The keyword is that I want to introduce at the end here. Not going to detail yet because we are still working on, but it's scalable optimization. Mean that if you have a lot of input, then what we can do can we do besides that. So this is come to the help that quantum inspired algorithm. That the keyword is the scalability. For example, that if I already show you example earlier that he will have only small like data point of the thing to for logistics that you send things the package. If you don't have a lot, then it's not a problem. But you have more like only 20 point to optimize that, you take forever to calculate. So with that, you need to use article algorithm that not maybe necessarily get the best part, but you need to lose some of the efficiency. So this, if you have this kind of thing that let's say that in terms of 10, 20 or 50 parts, if you have like 100 or 1,000 EV car that you want to optimize for energy storage, then you just get it. You cannot use the normal linear programming anymore. In that way, that quantum computing maybe come in. But at this point, is a quantum inspired algorithm that use some of the digital computer that already designed for this kind of optimization, like which is Huawei or some other company that already put some effort to that. That is some of the possibility that the opportunity that into this area. So with that, I think today will be just introductory and hope to maybe discuss more later. Okay, thank you.
All right, thank you, Dr. Worawat, for the wonderful presentation on the electricity grid optimization. So now the session is open for question. Any question, then we can discuss further. Any question from participants?
I don't believe so. Dr. Toigo, Christina, is that hand from the previous question? Or
I think it's from the previous question.
Okay.
Dr. Christina, I think you have raised up your hands. It's for the previous presentation, I guess.
Yes, it was from the previous one. Sorry, I forgot to take it down.
No problem. Always best to double check.
Any other question? I do have a question for Dr. Worawat.
Okay,
could you explain a little more that how the VPP works for the fluctuation on the electricity? That part is not very clear for me.
In the presentation, so the fluctuation come from like you have an on-grid solar cell, right? Normally, if you want to put the energy from the solar cell to the grid, you need to increase the voltage more than the grid. So that, I mean, if you have one, it's fine. But if you have more, like 10 house, sometimes it's competing. So this one to increase to that one to increase to each one keep increasing and so on. So eventually it will be past the threshold, and then the inverter will just turn itself off. And this can be, if you not have a lot of this in the grid, then you have this kind of fluctuation. These are the simple, like the small, I mean, the early problem that there could be more problematic with other things.
All right, thank you. Got it. Any other questions? All right. All right. If not, then
thank you.
Thank you, Dr. Worawat. We'll go for the next presentation from Professor Parvathy. Dr. A.K. Parvathy is a professor in Electrical and Electronics Engineering Department at the Hindustan Institute of Technology and Science, India. Dr. Parvathy is going to give a talk on innovation and the transition towards net zero emission, which is very important in the current energy crisis scenario. I welcome Dr. Parvathy to do a presentation on the topic. Please welcome.
Hello, thank you all. Thank you, Dr. Mariyappan sir, for giving the good introduction about myself. So I'll share the screen. I hope I'm audible to all. I'm sharing the screen now.
Yes, you are audible, and we are waiting for your screen to come on.
Is it visible?
Yes, ma'am. Please put it on the slideshow mode. And
that's right. That's right. Okay, thank you.
All right, thank you, ma'am.
Yeah, thank you. So, hi, good afternoon, one and all present here. I'm very excited to present my topic on innovation and transition towards net zero emissions. So this is a very hot topic, we should say. So I first acknowledge Royal Academy of Engineering UK for sponsoring a project in collaboration with University of Leeds, which led to some good results, which I'll be discussing in this lecture. And I thank the researchers and authors for the referred literature and WTUN for the opportunity, and one of my research scholar, Ms. Paushali Pal, who has worked on this project. So this is about myself. I am professor in Hindustan Institute of Technology and Science, and my research interest is on renewable energy system, power system, etc. And I have published 53 journal papers in Scopus indexed and SCI indexed journals and conferences. So the outline of my presentation is the need for net zero emissions, attributes of net zero as a frame of reference, virtual power plant scenario, need for virtual power plant optimization, existing marketing models and objectives. So first, let us see what is net zero emission. So the meaning of net zero is it refers to a balance between the amount of greenhouse gases that's produced and the amount that is removed from the atmosphere. So it can be achieved by a combination of emission reduction and emission removal. So this comes closely to the Sustainable Development Goal 7, which aims to ensure access to affordable, reliable, sustainable, and modern energy for all. So the need for net zero emission. So for the past, say, 10 years or 20 years, all of us are experiencing scorching heat waves, record wildfires, rising seas. So these are the climatic changes which are caused directly due to your greenhouse gas emissions. So we need to slash it to half by 2030 and reach net zero by 2050. So this is the conclusion which all the countries have signed in the Paris Agreement. So to reach the net zero by 2050, and the strategies to shrink your carbon footprint could be to reduce the emissions to close to zero as quickly as possible. So this could be done by phasing out the coal, investing in clean energy, shifting to electric vehicles, protecting the forest, and reduce the food loss and waste. And when we talk about removing the carbon from the atmosphere, so we need to pull as much as carbon as we pump into the atmosphere. So naturally, we can do it by planting trees which absorbs carbon, deploying emerging technologies such as direct air capture, so that this could be captured. Carbon could be stored in the geological formations underground. And the commitment from various countries are given here. So you can see that certain countries have already achieved this net zero emissions. Say, for example, Suriname, Bhutan, etc. have achieved it. And in law, it is there in certain countries, and it is a proposed legislation in certain countries. So by 2050, hopefully, most of the countries would have achieved the net zero. As far as India is concerned, we have committed for 2070 to achieve the net zero. So what are the attributes of net zero as a frame of reference? So what are the points which we have to consider? So first we have the front-loaded emission reductions. So we know that most of the emission is happening when we are directly connecting to energy. So we need to encourage the early emission reductions. Governance experts recommend the combination of long-term net zero commitment with short-term interim targets. So IPCC has identified over 200 scenarios to bring down the greenhouse gas emission. Now, when we talk about comprehensive emission reductions, we should understand that we should focus on the harder to treat sectors like heavy industry, buildings, food and agriculture, aviation and mining, etc. And where the zero carbon solutions exist, but they are extremely costly. So a comprehensive approach requires involvement of all the stakeholders for this process. Coming to the cautious use of carbon dioxide removal. So carbon dioxide removal will be probably constrained by the cost consideration and the geopolitical factors, biological, technological, and institution limitations. So a regulatory framework for the deployment of removals are yet to be developed. So this is a point which we have to consider. Coming to the effective regulation of carbon offsets. So the need for social and environmental integrity in carbon dioxide removal is linked to the integrity and appropriate regulation of the carbon offsets. So the honesty of the stakeholders and the countries plays a very important role in addition to the policies that are formulated. Equitable transition to net zero. So we should understand that the fairness of net zero depends on how the burden of the meeting the global target is shared across countries and within the countries. So certain countries have already achieved the targets. Certain countries are in a very short time to achieve the target. So it would be net zero globally only if all the countries contribute equally and fairly. Coming to the socio-ecological sustainability, the climate change is one of the several pressing socio-economic scenarios, challenges, and it could be called a threat multiplier. So a nature-based solution is more suitable for achieving an ecological balance and sustainability. Finally, we have the new economic opportunities. So net zero transition requires large-scale changes in the way economies are run, the skill, the demand, and the capital assets they require. So these are the attributes of the net zero, and it is a long way to go for in terms of research as well as policy making and application. So coming to the project which we have done, which is sponsored by Royal Academy of Engineering, UK. So our university is very much towards this achieving net zero. So we are contributing in several ways as in terms of research, and we have a 450 kilowatt solar power plant, and most of the maybe 40% of the load is covered by this power plant. So this is a project which we have done in collaboration with the University of Leeds, and we have already seen as previous speaker talking about the virtual power plant. So I'll just go through what is the scenario for this virtual power plant. We can see that there is number of increasing number of generators from the renewable energy and the issues of solar and wind energy like intermittent generation, increase of energy storage is just still a problem when we talk about the integration, and the grid fluctuation, which leads to the price uncertainty, and increase in the prosumers will lead to the more fragmented market. So virtual power plant is an answer to the renewable integration business model, and it is fast becoming a business model for utilities worldwide. So what is a virtual power plant? It is a cloud-based distributed power plant that will aggregate a collection of distributed energy resources, energy storage devices, controllable loads, and managed by energy management system. So this could be considered as a single power plant, though it is a distributed power plant. So the main part is played by the aggregator, who is going to have a direct linking with the market as well as with the distributed energy resources. So the hybrid system in different locations could be controlled by a virtual power plant, and aggregator makes the contracts with each DG owner. Thus, the aggregator acquires the chance of contributing in the electricity market with a reliable power quality. So existing power plants, virtual power plants are there in Europe and in Australia. And the optimization of virtual power plant, we can think of optimization by having a charge, optimizing the charge discharge rate of the storage devices, generation of DG units, and the energy purchase from the market. So if you want to optimize or maximize the profit, we should be purchasing less power from the market, and we should be supplying the power or selling the power when the market price is high. So various methods of optimization are there. For example, maximize the profit, minimize the power loss, emission reduction, and cost reduction. So the existing models are there, and the role of energy management system. So what are the market models we have? We have a day ahead market where we have strategically we are participating in a day ahead market by deriving its bidding strategy 1 day in advance and on an hourly basis. You have the real-time market where the smart dispatch of the electricity market, it is near real time, and this requires the two-way communication with the market operator and the available real-time information like your market price, actual renewable energy power production, etc. Then you have the unified electricity market, which optimizes the electricity trading in the day-ahead market to maximize the profit of the selling electricity and minimize the cost. So we have to, the electricity purchased in the day-ahead market need not be equal to the forecasted load, and hence the flexibility of the DG, ESS, and IL in the market in VPP is considered. So the modeling of uncertainty, so I'm sure we have to think about the uncertainty like your day-ahead market price, real-time market price, renewable energy power production. So we cannot neglect the uncertainty if we are considering the operating cost of the VPP. So stochastic programming approach can be used for modeling the uncertainty by a set of scenarios, or a robust optimization approach can be used for representing the uncertainty in confidence bounds. So what is the objective of the project? To minimize the consumption of power from the grid during peak hours, to maximize the profit of VPP by selling the power during the peak electricity demand, to minimize the environmental issues such as greenhouse effects, and encourage the use of renewable energy sources. So this is a problem description. So we can see that this is what we have done in the as part of the project. So it is a day ahead bidding, and the inputs are from the forecasted generation and the forecasted load, and the real-time pricing is also there. And we have a set of PV, wind turbine, micro turbine, fuel cell, battery, etc. And the schedule for the day ahead is predicted based on the optimization we have used. So this is the objective function which we have used, where we are considering all the sources which we have spelled here. And also the constraints is there, where we assume that we are having both charging and discharging of the battery, and the total power generation plus the grid should be equal to the load plus the power taken for charging and after the VPP. So the simulation results I'll be presenting over here. the system is considering the wind turbine, photovoltaics, PV cell, fuel cell, microturbine, and a storage battery. And hourly forecasted market price and the commercial load data is presented for the PV and WT power generation. So these are the, this is the considered thing. We are assuming the microturbine with minimum 6 and maximum 30 and others accordingly. And this is the dynamic pricing of the utility. So we can see that from the hours of say 7 hours to around 17 hours, you have a high dynamic price. So this will be the best time for the virtual power plant to sell to the market so that he can maximize the profit. And during the period which is apart from this, he can use it for charging the batteries, and during this period he can discharge. So this is the commercial load data which is required, and these are the forecasted power output from the wind turbine and PV. So 3 scenarios are considered when first scenario, all the units are in service. Second scenario, PV is assumed to be in off mode, and third scenario, fuel cell and battery are assumed in the off mode. We are using fruit fly optimization algorithm. So this is the bio-inspired algorithm from, it is proposed by PAN. So we can see that over here, the direction of the food source will be explored first by the phosphorescence organ, and the fruit fly will then fly towards the location. So this is the representation of the fruit fly optimization algorithm. And this is the first scenario result. So we can see over here that during the period, during the peak period, the power is maximum of a battery is used. All the power generation is happening during the peak period. And during the off-peak period, the battery is charged. And during the peak period, the negative grid power shows that power is being sold to the market so that we can maximize the profit. So this is the first scenario. And we can increase the market bid by having the storage battery discharged during the peak period. So second scenario, we can see that PV is in the off condition. And here also we can see that the power is sold to the market, and the other things, other constraints are met over here. And we can see that PV is not working. So it is in the off mode. This is a third scenario where we have the battery as well as the FC, which is going to be in the off state. So here also we can see that since we don't have the battery, we cannot be selling the power maximum during the peak period. Only the other wind turbines and the micro turbines are in operation. So these are the different results for the different scenario. And from this, we have concluded that for different scenarios, we will be able to, and this was implemented in the campus as part of the project, not only the simulation. And the conclusion for this presentation, we come to the conclusion. We have discussed about need for the net zero emission and what are the attributes of net zero, what is the need for VPP and VPP concept and definition, and optimization of VPP and objectives of VPP. So this is my presentation on net zero emission and virtual power plant. These are the references for my presentation, and thank you. So I would be happy to take questions if there are any.
Yeah, thank you, Dr. Parvathy, madam. Any questions on the net zero emissions from the audience? Questions?
We haven't received any in the Q&A. If anyone would like to ask a question live, they may do so. You can raise your hand. And if not, may I propose we move to the next speaker?
Yeah.
Thank you. Thank you all for the patient listening and cooperation. Thank you.
Thank you, ma'am. We will go for the next presentation from Dr. Patcharawat from Department of Mechanical Engineering, King Mongkut University of Technology, Thonburi. Dr. Patcharawat obtained his PhD from Osaka University, where he modeled the automatic responses using combined model of mass transfer and equivalent cycle to include various effects of non-Faraday currents. His is going to talk about the heterogeneous electrode structure for future electrochemical energy storage and conversion system. Dr. Patcharawat is working on electrode modification in the performance of electrochemical devices, energy conversion in fuel cells and batteries. So I request Dr. Patcharawat to start his presentation.
Thank you very much for your kind introduction. Could you hear my voice clearly?
Yeah, everything is clear.
Okay, that's great. Okay, my name is Patcharawat Charoen-amornkitt from Universiti of Technology, Thonburi, Thailand. I have a presentation in the topic of heterogeneous electrode structure for future electrochemical energy storage and conversion system, which is the research topic that we collaborate with Osaka University. Right. So as you all know, there is a need for the transition to renewable society that use large amount of wind turbine and solar panels. Typically, this kind of society need battery and fuel cell as energy storage or energy conversion device, while both wind turbine and solar panels could play a crucial role in the transition to cleaner energy. They encounter a common challenge. The wind doesn't blow consistently and the sun isn't always shining, making the energy production intermittent. And consequently, there lies a need to store the energy they generate for use during period of low or no generation. This is where battery and water electrolyzer play pivotal role by storing the power produced by the wind turbine and solar panels, ensuring a continuous energy supply. And despite the high demand for this energy device, the availability of raw materials is limited and come at high cost. Consequently, there is an urgent need to enhance cell performance to facilitate widespread commercialization and ensure sustainable development in the field. Before getting into strategy for improving device performance, let's examine the schematic diagram of various devices that I show here. Despite the difference in the mechanism and chemical solution, this device operate under share principle. The fundamental process involves the reaction occur at the electrode material with the electron transferring through the external circuit and working electron moving through the electrolyte to another electrode. A critical factor influencing the success of this reaction is the architecture of the electrode, and presently, most electrode consists of uniformly distributed material. Now, the question arises like, how can we enhance the cell performance? In the electrode of the electrochemical energy device, as mentioned earlier, there are several processes occur, including electrochemical reaction, mass, heat, electric charge transfer process. For example, for the water electrolyzer that I present here, the electrode performance will be related to the charge transfer rate as well as the water supply and the product discharge rate. In this case, it is the oxygen discharge rate. There is a trade-off between this rate and transport process, and this trade-off lead to the optimization problem. And the main goal of our research group is to find the optimal product structure that enhance the overall system performance and fabricate it. Improving the cell performance can be achieved directly by modifying electrode. If you have a look onto the previous study of the electrochemical energy device, you will see that people attempt to modify electrode structure in order to reduce the irreversible loss. There are plenty of examples, including works in lithium-ion battery, polymer electrolyte fuel cell, and vanadium redox for battery. It helps improve the performance considerably. The reason behind the improvement of all devices is similar. The hole or void that created improve the mass transport. For example, the hole would help water removal in a fuel cell. Although the performance of the electrochemical device has been successfully improved by various approaches, the research is proceeding without knowing the limitation of the improvement, as this investigation has been predominantly characterized by a trial and error methodology. So not only those work are based on the trial and error, but they also attempt to tackle the optimization problem with experiment. Instead of tackling the issue through the experiment, which is costly, our research group tried to develop our own model to tackle the issue with lower cost. For example, in this work, this is a work from the senior project of the bachelor student in our department. They developed their own 3D isothermal model of polymer electrolyte fuel cell and implemented through some computer coding to simulate the transport phenomena occurring within the electrode that incorporate micro-scale crack. This study aimed to investigate the impact of the distribution of this crack, and prior study has like a comprehensive method for evaluating the significance of these cracks. And by exploring their effect and considering their potential synergy with the artificial layer perforation, this study provides valuable insight into the optimization of the electrode structure. Also, the performance of the electrochemical device has been successfully improved by various approaches, experimentally and numerically. The limit is not clear. For the electrochemical device, we do not have anything like a Carnot cycle for the heat engine that operate between two temperature limits. And therefore, research is proceeding without knowing the limitation of the equipment. And we come up with a question like, what is the minimum value of irreversibility that can be achieved by their spatio-temporal structure? What is the spatial temporal structure of the electrochemical reaction transport site that minimize the irreversible loss? So if you have a look out there, mathematical optimization is extensively used in various engineering disciplines to design better systems. Also, the optimization is not, of course, not theoretical limit. They can provide us the result of at least somewhere closer to the theoretical limit. Therefore, it is a promising approach to design the porous media structure. And this kind of optimization can be categorized into three methods: sizing, shape, and topology optimization. Each of these methods has a focus on different aspects of the structure. Among this optimization, topology optimization is an approach to optimize the structure layout within a given design space in which the layout can be any shape. Its advantages are that it has a higher degree of freedom and outperforms the other method. Over the past decade, researchers in numerous engineering disciplines have become increasingly interested in the topology optimization techniques. The optimization process is carried out to maximize performance under a set of predetermined conditions and constraints. Topology optimization has now been applied to more complex systems with multiple physics, including heat and fluid, after initially being used in structural mechanics. Here are some examples applied to the electrochemical energy device, like the work on the left, Yachi et al. They performed the topology optimization for the full field in vanadium redox for battery using a two-dimensional pseudo-analysis model with a simplified formula for the electrochemical reaction. The optimization problem is defined as a material distribution problem concerning the electrolyte and permeable material. The result reveals the optimized design is the type of interdigitate field in which the branch channel are disconnected. Or another example would be a published paper on the right from the research group in my university in Thailand. They utilize the multi-objective topology optimization to design a cooling plate for the battery thermal management system, considering the effects of heat load from different charge discharge rate on the optimized flow path. And topology optimization has a remarkable potential to develop a groundbreaking structure that can outperform the conventional electrode due to its broad applicability in achieving optimal engineering solutions. However, only a few studies have demonstrated how topology optimization can be used to develop a novel design for electrode with heterogeneous structure. It should be noted that conventional design strategies aim to achieve a uniform distribution of the material. However, research suggests the performance can be significantly improved by adopting the heterogeneous design approach. By converting the concentrating the distribution of available material where it is most needed. Topology optimization lead to more efficient utilization of resources and then boosting the overall cell performance. And here are the example of our study. However, on the side note, we are not just using topology optimization. Our concern is that topology optimization is just a numerical approach which relies on various factors, including the objective function, algorithmic methodology, and tuning parameter. Consequently, it becomes crucial to establish a solid theoretical foundation to support the optimized solutions. And in this context, we postulate that the optimized electrode would align with the system characterized by minimal entropy generation, drawing inspiration from the widely employed entropy generation analysis in assessing the thermal system. And we have shown that how the topologically optimized structure of the porous reactor can lead to more uniform and minimum entropy generation. And building upon this work, we are trying to address issues in several applications. For example, polymer electrolyte fuel cell, proton exchange membrane water electrolyzer, and vanadium redox flow battery. Please allow me to roughly provide you an idea of how we conduct our study. The example I show here is the proton exchange membrane water electrolyzer. When we address in the optimization of the electrostructure of water electrolyzer, we have to develop the model. And in this case, it will be an electrode operating under the isothermal and steady state condition. The porous electrode consider is composed of 3 constituents: carbon support catalyst, electrolyte, and void. Water enters the electrode from the inlet boundary where it is converted into oxygen and proton at the triple phase boundary, and the pore are responsible for transporting water to the reaction site and oxygen out of the reaction site, while the electrolyte facilitates the transport of ionic charge, and the carbon support catalyst enable the transport of the electric charge and decrease the activation energy barrier. For the optimization, the density method is employed. The method involves dividing the design domain into finite number of elements and assigning the material density value to each element. These density values are then used to determine the presence and absence of material within each element, and effectively creating a design with optimized material distribution. The optimization process consider the value fraction of electrolyte, carbon support catalyst phase as the design variable, with a goal to maximizing the average rate of the electrochemical reaction. So this objective is mathematically formulated as an optimization problem. And we have worked that we developed the coding for the optimization routine, but as the system is getting more complicated, we employ Thomson multiphysics to solve the governing equation and implement the optimization procedure as shown here on the left. The entire process is repeated until the convergence criterion, which in this case is the maximum number of iterations is achieved. And here is the example for determining the electrostructure of the PEFC. We first developed a two-phase flow model of PMFC, and then the model is coupled with the topology optimization technique to seek for the optimized constituent distribution in the catalyst layer. In this study, we consider a full cell as seen on the left figure, and the model is well validated with the experimental data from previous study. After the optimization routine, results indicate that an electrode with a heterogeneous structure can enhance the overall cell performance by balancing various transport and rate process. The performance enhancement is formulated as a higher voltage at even current density. This optimization problem is constrained in a way that the overall material amount used in the topologically optimized catalyst layer would be equal to that of the reference catalyst layer before the optimization. This is to ensure a fair comparison to answer the question like, if we have different amount of material, where should we put it so that the system will be more efficient? And this research handled by a research student at our lab aim to develop a model to integrate mass transport limitation arising from gas coverage in the anode catalyst layer of water electrolyzer and utilize it for topology optimization. This is because to make the water electrolyzer a widespread commercialization, we need to make it able to operate at high current so that the investment cost for per unit will decrease. We developed the model, and subsequently the model is employed in topology optimization to identify the optimal porous structure. And utilizing the console software, 2D models were developed for comparison with earlier model and conducting topology optimization to identify the optimal structure. The objective function here is the maximization of the reaction rate, and as you can see, the material volume fraction distribution gradually changed from the initially homogeneously distributed to heterogeneously distributed. Although conventionally, research aim to produce electrodes that are homogeneous and uniform, and finding has shown that by concentrating the distribution of available material where it is most needed, heterogeneous distribute structure lead to more efficient utilization of resource and increase the performance by 3 times. And for this study, from one of my master students, we would like to address 2 issues found in the vanadium redox 4 battery. Firstly, the cell architecture, which features the 4 channel on top of the electrode, has been widely adopted due to its superiority. However, during the scaling up, this design may lead to unnecessary thickness in the step, hindering the ability to achieve higher performance, higher voltage, and result in increased loss. And secondly, in previous study using the topology optimization to seek for the optimized design, the system was often simplified by focusing solely on the bottleneck electrode. And therefore, it remains unclear how the optimized design would be when considering full cell models. So in this study, we applied the topology optimization to the numerical model developed by our group, considering both electrode and the membrane. And the finding indicate that under a simplified fold-through design and the electrochemical reaction at the selecting operating point can be improved through the reorganization of the material distribution and the optimized electrode structure review are interdigitate type with the shape resembling a tree-like structure. This again signifies that such a heterogeneous structure significantly outperforms the conventional homogeneous arrangement. And consequently, this type of the structure holds promise as a potential path for advancing the performance of the redox 4 battery. Besides our research group, we also found some researchers utilize the topology optimization to create porous structure to create a porous electrode, which they found to perform better than the traditional electrode. And they apply this approach to redox 4 battery as well as the supercapacitor. But they do not limit their study to just utilizing the topology optimization. Their research group also demonstrate like how such a heterogeneous structure provide higher performance experimentally. After conduct a study that employed the topology optimization for design of the porous electrode, the design structure was fabricated using additive manufacturing techniques. And also at the moment, the resolution is not there. As the additive manufacturing continues to advance, it is anticipated that complex porous electrode design will be feasible for direct printing in the future. And heterogeneous electrodes are gaining increased attention due to their potential to significantly enhance performance while using less material. Recent publication in Nanoletters and Nature Energy within past 2 years has explored this concept experimentally. The finding indicates that such structure can improve performance significantly, while the fabricated electrode in this study may not be as complex as those obtained numerically. Ongoing effort within our research group aim to bridge this gap and experimentally demonstrate similar structure. our work can serve as a benchmark for researchers interested in fabricating such advanced electrode structure. And we believe that this type of structure hopefully means as the next generation electrode for electrochemical energy device. Okay, so for conclusion, the performance of the electrochemical device has been successfully improved by various approach to create a heterogeneous electrode structure, but the research is proceeding without knowing the limitation for the improvement. And the topology optimization was successfully employed in various electrochemical energy device application. Also, conventionally, researchers aim to produce electrode that are homogeneous and uniform. This finding has shown that heterogeneously distributed structure lead to more efficient cell. And recently, a field study demonstrate how to fabricate such a complex structure. And for future work, a further study on fabricating such a complex structure with a cost-effective method is essential. And such a study is ongoing in our research group. I would like to express my sincere gratitude to our collaborators from Osaka University, Professor Shishma, Professor Suzuki, and Mahel-san, and also my team, including the postdoctoral researcher and the heterogeneous electrode structure team at our lab. Thank you very much.
Thank you, Dr. Patcharawat, for a wonderful talk on the topological optimization for the heterogeneous electrode structure. We have received one question from our next speaker, actually, Dr. Christina. It's all about the electrolyte volume. Is it also possible to research its influence on overall stability and lifetime of a battery? That's a question.
I'm sorry. I'm sorry. I just like turned off my my microphone. So I'm wondering, like, in which application that Dr. Christina is focusing on? Probably fuel cell, right?
Well, I was mostly thinking about battery application for this part.
For the battery, right? Yeah, I think like if we have some kind of degradation model that we can account such effects into our model, we can use it as the objective function, and then of course we can use the topology optimization to like search for the optimal structure that would increase the overall stability or lifetime of the battery.
Okay, as this is always a super critical question about how much electrolyte is filled within the cell, and trying to break it down to as least possible, but nevertheless working well. So I think this may be an interesting question. Yeah.
Thank you very much.
All right, Dr. Patcharawat, before we go for the next presentation, I just have one more question. What will be the topological optimization effect on charging, discharging, or cyclic stability for a battery? Again, more or less similar.
Yeah, if I understand correctly, you are mentioning about like the topologically optimized structure, how it affects on the stability of the charge discharge performance, right?
Yeah.
Actually, we haven't invested on that part, and at the moment we just assume that our system is operating under steady state condition. So we assume that the cell voltage gonna be stable at all time. And I think yes, this kind of study is very important and essential for future study.
All right. Thanks for your comment, Dr. Patcharawat.
Thank you very much.
So without any further delay, we will go for the last presentation from Dr. Christina Toigo, is a professor of hydrogen technology and energy storage, University of Applied Sciences of Austria. Dr. Christina is going to talk about increasing the battery sustainability on materials side. So that would be a very important topic on the energy storage technology. Dr. Christina is performing research in the area of hydrogen technology, energy storage, with a major focus on battery electrodes and lithium-ion batteries as well. I welcome Dr. Christina to start the presentation.
Thanks a lot. I'll share my screen. Do all of you see and hear?
Yeah.
Wonderful. Okay. Thanks a lot for the introduction and all the previous super interesting and comprehensive presentations. For today, I would like to give a short and not too deep overview of what we are currently doing. Yes, I called it kind of increasing battery sustainability on material side, because we are mainly working on trying to replace those classically used, especially fluorinated polymers, by somehow more sustainable alternatives. This is also driven by the fact that we do have a new EU regulation concerning a very strict policy on PFAS, and therefore I thought this may be a good topic for today. So, I'm currently pursuing this professorship on hydrogen technology and energy storage systems, and today is kind of part of battery energy storage, lithium-ion, and some ideas beyond. So let's see, here is it. I know we're no longer in time. I'd like to keep it short. I'll give you a short introduction on my motivation and the background. I think not all of you are kind of aware how battery production is performed stepwise, so I will give you some hints here. We'll go on with some battery materials and their sustainability. And then I'll go to this point where we talk about bio-based polymers and batteries, followed by a short outlook. I brought a very personal thing here. This is my personal load profile from autumn last year. So on the upper part, we do have our electricity consumption. And on the lower part, we do have our production through photovoltaics. And I think nearly to what we heard, I think it was the first or second presentation when you also had this, I think it was 9 to 5 or 6 p.m. Where you only have the sun shining, and therefore you need to utilize any forms of energy storage system to also be able to use your electricity, your self-generated electricity over the night. I think every one of us is aware of the fact that we are kind of approaching a more sustainable energy production. We try to get rid of those fossil fuels, even though it may take more time than we expect or we calculated in the beginning. We now need to try to put all our renewable energy sources within the grid, especially thinking about photovoltaics and wind, where we really have a high fluctuability, which is rather hard to predict. And therefore, anyhow, we will have to think about energy storage systems. We heard a lot about hydrogen before. This won't be the topic here. Of course, it's an option. I will think about how to make batteries greener. So, of course, one is getting more and more of ecological aspects. I think ethical mining of raw materials is getting a really hot topic. I'm sure you came across Tesla and also the further big car manufacturers now getting involved in mining, buying mines, for example. The whole supply chain will be more and more under pressure, I think. We're also talking about safety aspects. I will come to this later. And of course, economic aspects, it's all about the money. So we need to think about materials that may be easier recyclable than PVDF and PTFE may be, a good availability and a good relation concerning cost and benefit. I just brought a small graph on how batteries are produced in a very first and simple drawing. On the very left, you see kind of a beaker where we do put in all our active material, our additives, any binder, which is kind of acting as a glue within the material. This is then dissolved in a solvent. Afterwards, this is kind of coated, so brought on any current collector foil. And afterwards, the solvent is evaporated once again. So we do only have our electrode materials upon there. One may see even at first sight that we need a solvent here and we need to get rid of it here once again. This is also one of the reasons why we are talking about a dry electrode processing. So just taking into account that the solvent may always be any kind of harmful or anything we need to add in the very beginning and then get rid of it at the end. So what I would like to talk about is this step as given here, so the so-called wet electrode processing. So we usually need any kind of solvent. Very often this is dependent on the type of binder. And classically, we are using fluorinated polymers like PVDF, PTFE, also SPR, which is not a fluorinated polymer, is a very standardly used binder here. And there are, of course, alternatives. For example, any biopolymers. I brought some of them, which may be guar gum, CMC, carboxymethylcelluloses, gelatin, alginates, and many further. So cellulose-based materials are also of relevance here. So just to clarify, of course, fluorinated polymers have to be produced in a chemical forms, and things like alginate, for example, may be produced by utilizing algae or any natural products, or thinking about lignin or cellulose-based things from plant fibers, for example. In most of the cases, most of the polymeric binders, so especially the fluoride ones, can only be worked with in a solvent-based way. So those polymers are not soluble in standard water as a solvent, and therefore we need to use any organic solvent. Typically this is, I'm sorry, I only do have the abbreviation here. This is NMP, this is N-methylpyridone, which has a certain toxicity and is nothing anybody really loves to work with. Going along with this standard solvent, with this organic solvent, one has to, of course, think about occupational safety, of explosion-proof devices, of recycling, of protecting workers, of course, from the solvent. And on the other hand, of course, you would be super free to also just use water-based solvents. Therefore, we should get one step back and therefore think about which binder types are soluble in water. So maybe not, those are not those PTFE and PVDF binders, but most of these bio-based binders are soluble in water. And therefore, you would not only be able to kind of replace a fluorinated polymer by a bio-based one, but additionally, you are also able to replace the toxic solvent by just water, which is also just think about processing, about buying anything and recycling, which is way easier to process than an organic-based one. As a typical example, I brought sodium alginate. I'm not sure if you came across it already. It's made from brown, or it's extracted from brown algae. So it's also a natural product. It's a well-known chemical and is for many, many years or even decades been used in textiles, in food. For example, have a look at your yogurt, for example. Very often you have a kind of this E401 as an additive within your yogurt, maybe to stabilize it in its forms as it is. It's also used in biomedical and cosmetics, and its use within chemistry or technology is only just arising, as it may be one possible idea for this. Now I brought some possible application areas of this sodium alginate to be used in batteries. On the very left side, what I already mentioned before, it may be used as a polymeric binder, to make all the active materials stick together, and not only stick together, but also stick on the current collector foil, which is a metallic and very, very flat and plain surface, and it makes it very hard to stick a standard powdery material on it. That's the one possible application area. And you could also kind of fabricate separators by, for example, using tasks like electrospinning or any fiber producing technologies. So that's also something that's really currently under research. A separator, I don't know how well versed you are in the battery field. A separator typically consists of polypropylene, polyethylene, or layers of those. So it's also, well, it's a plastic, it may be crude oil based, and anyhow, of course, it's kind of disadvantages for battery recycling afterwards. This sodium alginate, so this is only one example. We could do the same thing for cellulose-based things or ketene-based chemicals or polymers here. Most of them are suitable for all those ideas. So you may also use it as an electrolyte, or at least an electrolyte additive here, especially for those future battery systems concerning sodium ion, zinc ion, magnesium, and aluminium air. I just read a paper recently working on sodium alginate also being suitable as a membrane, or at least additive, for fuel cell applications. So what you can do with your sodium alginate, you can in principle do the same standard processing as you do with a classical solvent-based battery electrode. So you do these mixing steps just within water as a solvent, you do a coating, and afterwards you evaporate your water. Nevertheless, what we found out is that we do have a special rheological behavior within the slurry. With the standard binders, you just kind of mix your slurry, which is then the mixture of all within the solvent. You can usually have it standing there for hours and nothing happens. If we are now talking about biopolymers, and especially about sodium alginate, you see that we do have a very, very high rate of demixing, especially you can see it on the very left side. That's of course not that advantageous. So it's also, a time thing. You need to mix it, and suddenly after mixing you have to go on with the coating step, because otherwise it's kind of settling and all your mixing step was for nothing. So this is something we had a closer look at. We also prepared some electrodes out of the sodium alginate mixture. What we found out was that they do inhibit they do have a good mechanical stability. So concerning about banding and peeling tests, for example, they also do have a very good electrochemical performance. We can see here on the left. So there was one really working bad, and the other examples really performed well, also over a high well, a little high amount of cycles of around about 100 cycles. Nevertheless, we are still need to work on this slurry stability. Currently, we're kind of trying which additives may be working positively here, but of course, it doesn't make sense to replace fluorinated polymers by a biopolymer and then add another kind of highly technical or highly toxic substance as a kind of a modifier here, because then in the end we didn't get anything. So this is what we are currently working on, increasing its stability without adding, once again, anything that's kind of harmful or won't be super positive here. Same here for example for solid state batteries, where you do have an electrolyte, which is somehow a mixture of electrolyte and separator, working as both of it. You may, for example, insert this alkali salt within the whole polymeric matrix and thereby increase its ionic conductivity. So especially for future battery systems, this may be a great idea to, kind of from the very start on go into this direction. To conclude, I think that's a topic we all are aware of. We do have an increasing demand for energy worldwide scene. The use or the utilization of renewable energies just goes along with a higher required amount of energy storage systems, and therefore we really have to think about which resources we use, and in best case, of course, we use any highly available, non-toxic, and in the very best case, also cheap raw materials. Thanks a lot for your attention.
All right, thank you, Dr. Christina, for a wonderful presentation on the increasing battery sustainability on material side. Now the talk is open for any question from the attendees. Any questions we can discuss now? Anything from the participants? Any questions, any comments? And we can go ahead now.
I think our attendees may be a little shy about asking questions.
I just wanted to start with one question to Dr. Christina. You were talking about the multiple use of sodium alginate as a binder, a separator, and electrolyte or additive in electrolyte. If that is the case, I'm very much interested to consider that as an electrolyte or some additive in electrolyte to improve the mobility, charge carrier mobility. If that is the case, I just wanted to know what is its redox potential?
I just didn't understand your last two words. The best what?
The redox potential of
it depends. Even concerning sodium-ion batteries, we are having both organic electrolytes, and we also do have water-based electrolytes. So, of course, being a water-soluble binder, sodium alginate and most of bio-based polymers won't be applicable for aqueous sodium-ion batteries, as they will just dissolve within time. That's least problem for organic-based or kind of those typical electrolytes. Currently, I do not have any data on its redox potential. I'm sorry.
Oh, no problem. I'm just curious because it can be considered for PV devices as well. That's the reason I asked. And one more question.
Okay.
You showed a plot, specific capacity with respect to number of cycles, 100 cycles. Yeah. So
Yes.
what are the different, I'm okay with the top 4 curves and why that bottom 2 falls down after 60 or 70 cycles.
This one?
Yes, the blue curve, the cycle number after, yes.
So first of all, this was incorporated in LTO, in lithium titanium oxide cells. So concerning the specific capacity, which is around about 160 to 170, and we used different blends. So we had a only sodium alginate battery, which was in fact the blue one. So this one was only containing sodium alginate as a binder, and we could see that it's not optimum, okay? And the two other ones, the yellow and the purple one, are kind of blends with a styrol butadiene, with CMC. So with this carboxymethyl celluloses, which was honestly not our initial idea, but it seemed to work out very well. And by now we do have nearly 3,000 cycles and they're showing a very, very high stability.
All right, thank you. So we can go for other questions if there is any. Any other questions? If none, then I hand over the session to Tennessee. Thank you.
Thank you all so much. If I may, I would just like to thank all of our esteemed speakers and our chair for today's event. It was fascinating. Not being a scientist myself, some of the content probably went a little over my head, but we had a lot of attendees staying with us throughout. So I appreciate those of you particularly who are in East Asia and it's well into your evening now. We'd just like to thank you so much. And also to thank our WTUN member universities for enabling us to convene you all here today. So just a thank you to Hindustan Institute of Technology and Science, for King Mongkut's University of Technology Thonburi, Suranaree, University of Technology, University of Applied Sciences Upper Austria, and finally University of Technology Malaysia. I'm not going to keep you much longer. I know we are a little over time, but I just wanted to just remind everyone the reason that we were here, which was to recognise the International Day of Clean Energy, which is actually tomorrow, 26th of January, declared by the General Assembly resolution as a call to raise awareness and mobilise action for a just and inclusive transition to clean energy for the benefit of people and planet. And I feel that this has been well represented across each of the talks that we've had today. The International Day of Clean Energy was the perfect platform upon which to demonstrate a few of the many, many ways that the universities whose membership constitutes the World Technology Universities Network are each committed to driving inclusive, sustainable innovation in their education of the next generation and also the research practices. If I may promote upcoming WTUN events and opportunities for further collaboration and knowledge transfer, I'd just like to announce that the World Technology Universities Network will be celebrating World Engineering Day for Sustainable Development during the week commencing the 4th of March 2024. And during this week, we will convene multiple events aligned with the 2024 theme, which is Engineering Solutions for a Sustainable World. We hope that these will be hosted and supported by universities across our broad membership. So please do keep an eye out for those. We'll be advertising them and also disseminating via your institutions. Additionally, if you have any, if our speakers, any of our attendees, or indeed your colleagues have any ideas or suggestions for an event that we might include during World Engineering Week, please do not hesitate to contact us. And as I picked up on multiple synergies and areas of interest perhaps that go across our institutions, if I may, Chair, I will just finish by sharing just news about our one of our activities that is live currently, and I will just bring this up now, just bear with me. Okay, hopefully you can all see that here. This is on our website, so you can go to WTUN.net and you'll be able to find this. But this is just a reminder that we have an exchange program each year. It's currently live and active for applications. And for any member of staff, both academic or professional, or indeed PhD students at our member institutions, each institution can submit an application for two proposals to receive one of 18 grants for £2,000, so GBP, which is intended to initiate or help support or continue a collaboration between two of our member institutions. So the deadline is the 21st of March, so there's still plenty of time to be involved. And for the colleagues that are on the call, if you're interested in finding out more, you can get in contact with the WTUN directly or speak to your operational board member at your institutions, who will be able to advise on how you can be involved with that. That's everything that I had to say. And once again, thank you so much for your time, your attention and your expertise. And thanks again, Dr. Shanmugam, for stepping in and chairing this session. Thank you all.
Thank you, Dennis. Thanks a lot for everyone.